All right. Let me actually start the presentation. I'm doing an introduction to fuzzing. It's a pretty scuffed presentation, but we'll wing it, whatever. All right. I'm Sharad. I'm a fourth year CSEC here. I'm from like DC, that area. I work at 26 Technologies. It's like I do mobile mainly over there. It's in DC as well. DARPA shit. What else? I was previously at a company called Zelek, which does like blockchain research, and a company called High Peak Cyber, which is also on mobile. I contribute to libafl, which is a big reason why I'm doing this presentation. libafl is a fuzzing library. If you're familiar with AFL++, which is one of the predominant fuzzers right now, libafl is a library alternative to AFL++. I also contribute to Frida, which is a mobile hacking thing. I'm the VRIG and RE IG lead as well. All right. So what is fuzzing? Fuzzing really is just like the process of throwing random inputs. There's ways to make it less random and more not deterministic, but smarter in how you mutate your inputs. Throwing random inputs at a target and hoping something happens. And as we'll talk about here, fuzzing is much more than just like dumb fuzzing, which is throwing random shit at a target. These days, there's a lot of indicators that we use, which I'll talk about further, to make that process faster and more effective. That like a sphere broadly is what we call coverage-based fuzzing. I'll talk about it right now. All right, coverage-based fuzzing is the process of collecting what parts of an input run as a result. Well, what parts of a target run as a result of an input. So I'm thinking of how to explain this. So suppose you have some input like A, B, C, D, right? Let's say you throw it at a target. It's going to cause the target obviously in some way has to process that input. So the purpose of coverage-based fuzzing is to essentially track what parts of the code run when you run that input. And this is useful because this is a very useful idea, because when you throw an input at a target, you can basically, when you throw an input at a target and when you're fuzzing a target, you want to cover as much of the code as possible, and you want to run your inputs on as much as code as possible. So coverage-based fuzzing makes it possible to iteratively, through this feedback loop, run through every part of the target itself. Yeah. And it's been proven to be a very effective technique at crashing targets and finding bugs. All right, as a brief, like most of this presentation is also gonna be demos. It's just kind of just like a high-level background. Address sanitizer, or ASAN, that's a pretty key technique we use in fuzzing. The purpose of ASAN is to detect memory bugs, stack overflows, heap overflows, you have to freeze, etc. The way ASAN works broadly is that for every byte of memory, you also have a shadow region of memory that basically marks whether that byte of memory is valid or invalid. Whenever you make an address access, you check if that access address against the shadow region. If the shadow region says it's valid, it passes. If the shadow region says it's invalid, it crashes. It's pretty simple, and it's pretty much the predominant way to find a lot of these bugs. All right. I don't really want to make out a slide for this, but I'll just draw it out. So there's two predominant fuzzing modes that we use these days on this fork server, which is the primary mode used by AFL++. This in process, which is used by another piece of software called libfuzzer, which is LLVM based. Actually, they're technically all LLVM based, but libfuzzer was the original. Let's like draw this out. Fuck. What's happened? And actually test this. Please. This will actually suck if it doesn't work. There we go. Oh, fucking forever. All right. So fork server is actually pretty interesting how fork server works. It's a lot more complicated than in process, but it has its advantages. So you guys are probably familiar with the fork. So before I talk about fork server, let's talk about the fork syscall. If you've ever taken 201, you've probably used this. Fork, what fork does is fork creates an exact copy of the process. So for example, let's say process A. Process A has stuff like memory, it has threads, it has files, and it has like, I don't know, other stuff, whatever. If you run fork in process A, it'll create a brand new process that's entirely identical to process A. So you'll create a new process B, but it's entirely identical to process A. Now, due to a thing called copy on write, fork is actually extremely fast and extremely cheap. So as a result, you can fork a lot and it won't be that expensive and it won't take very long, which is very nice. The way we do fork server basically is we start with our fuzzer at the top. This process basically is the top level process. In this case, it's going to be AFL fuzz usually, which is the AFL plus. The fuzzer itself does stuff like data collection, corpus management, which is basically just managing your series of inputs and what inputs you're going to use, as well as, which is the key one, is mutation. So it'll mutate the inputs every single run. Now, to essentially fuzz the target, what AFL fuzz will do, or your fork server, it'll actually create a fork server. So what it'll do is it'll fork the fuzzer and then exec v your target. So if you recall, probably like 201, exec v, what exec v does is exec v will, for example, take a process B, for example, take process A, I guess. If you exec v in process A, it'll entirely destroy process A and replace process A with the process image of process B. That all happens kind of in place in memory. The purpose of exec is basically to start new programs. So typically, your loop that you usually use is you fork first, and then you fork to create a new process, and then you exec to run your new process in that process. All right. So what it'll do is it'll fork into a new process here, and it'll exec the target. So what the result of that is a target is now running here. But actually, this target right here, the target is a thing we're fuzzing, by the way. This target right here is not actually what will be fuzzed. This target is what will serve as the fork server. And every time the fuzzer wants to start a new run, it'll refork itself and create a grandchild process. So I guess in this case is a child right here. Create a grandchild process, which is, because we're forking, it's exactly identical to this target process right here. So to create an identical grandchild process here, and this will actually be fuzzed. Yeah. This has a few advantages. So firstly, fork is not as fast as in process. It's like quite a few orders of magnitude slower than in process. And the main reason for that is because forking, even though fairly cheap, is still takes time and still somewhat costly. It's not as like expensive as like Windows operations, but it still takes time, and it'll like at scale you'll see the difference. Your child, you got a fuzz target here. The one advantage to this is that if this fuzz target crashes, your target, your fork server, and your fuzzer are not affected, which is very nice because then you don't have to restart your fuzzer and your target, and your fuzzer and your fork server. That's the main advantage to it. Fork server mode is also very effective at fuzzing basic command line targets. It works very well at doing that. And fork server really is the predominant way to fuzz these days because it's very easy to set up. It just kind of works. There's ways to make fork server faster. One of those ways is persistent mode. Also, I guess one thing I forgot to mention, the primary advantage of fork server is the fact that you don't need to reset your target. So, as we'll talk about with persistent mode, if you try to fuzz the same process over and over again, it's possible that could be artifacts left over. I guess if you don't clean it up properly, it's possible that could be artifacts left over from a previous run. So for example, let's say there's a global variable that it sets, then if in a previous run, in a previous fuzzing run, it sets that global variable, and you don't unset that global variable between runs, then it's possible that next run, that global variable is still going to be used, and that's a problem because that means that your fuzzing process is not the same for every single run, which makes crashes really, really hard to triage because you aren't running the same state every time. So it's possible that a crash is built up over previous runs, which is not a good state to have. That's the main advantage of fork server. You don't have to deal with that problem. Yeah. Persistent mode kind of breaks that paradigm. You have the same deal here. You have your fuzzer here. You have your target here. And then, so this right here is going to be your fork server. And then your target, you have your real target. So your fuzz, this right here, I suppose is now your fuzz process. So with fork server, every single run, it reforks this process right here. With persistent mode, that changes. With persistent mode, instead of reforking every time, it'll rerun in this target for like however many times you tell it. For example, if you do persistent mode 100 times, instead of reforking every time, it'll keep this process open between runs for 100 times. That's it with persistent mode. But the problem is you face the previous problem that we're dealing with process state being left over between runs. Because this is now running the same process in the same memory state, in the same memory space over and over again, you could have artifacts left over from previous runs in your persistent mode process, and that leads to problems. So you need to do a good job. You have a really good understanding of your target, and you need to do a good job to make sure that you actually clean up your target before you rerun a new persistent mode run. That's kind of persistent mode. I mean, that's kind of fork server mode with persistent mode. There's other bigger advantages and other optimizations you can make, like shared memory, but that's a different deal. I'm not going to talk about that here. All right. The final mode, I guess, I might as well move this slide, whatever. In process. In process is running in the same process, literally. So your fuzzer and your target are in the same process. So if I this up here again, it's gonna take fucking forever again. Oh my god. There we go. So in memory mode, basically is this. So as we saw here, you fork target and you fork again your target. And in memory mode, you instead run in the same process. So you have in memory here. So in this case, your fuzzer will be here. Your target will be here. basically in the same exact process. In your fuzzer, instead of forking and calling the target, it'll directly call the target over and over again. This method is primarily only effective for libraries. Like, for example, let's say you're fuzzing like libpng. That's primarily the main method for it. Yeah. Cool. That's in memory and in fork server. So let me do a few demos here to kind of describe the fuzzing process. All right. So I'm going to create a really simple target that's actually a little challenging for a fuzzer, for a dumb fuzzer, I guess, to find. So just like rip this shit real quick. Test target. C. I should include ST. Val scanf. Yeah. So if val is equal to aux and bb60, then abort. All right. So this target right here is actually pretty hard for like a standard dumb fuzzer to crash. The main reason for this is that you need to it's a really simple target. It doesn't do much. It just takes in a single single integer, and it compares that integer against A, B, B, C, C, D, D. If you find that specific integer, it crashes. This is really challenging because you have exactly a 1 in 2 to the 32 chance of finding this correct target. Find this correct number with a dumb fuzzer. We'll see that a normal fuzzer finds this really, really quickly, actually. Actually, I'll make a modification here. What is it? What's IAF? God damn it. Give me 1 second. Until IAF. Info plus. Oh, enable this. Split switches. All right. I believe this is it right here. So when we're compiling a fuzzer, well, we're compiling a fuzzing target, specifically AFL++, we're using a thing called AFL playing fast, which is basically AFL playing fast is a wrapper for just normal playing, and it uses a thing called LLVM passes to essentially instrument the target. I'll talk about more what the instrumentation does a little later. Oh, this works. My LVM broke. Okay, my LVM is not broken. Thank God. All right. So we'll see that. Oh, I gotta start input directory. Inputs, outputs. Actually, 1 second. It's a random input there. Nothing crazy. Fuzz time H dash I corpus dash O is your out. I believe you just do this. That's it, I think. And that's it. What the fuck? Oh, I need core pattern. That's cool. Let's see if it finds it. Oh, okay. Will it find it? I'm gonna fuck this up. That's 6K execs a second. That's like not bad. What did I mess up? I messed up something. Yo, what the fuck? Just like can't see that shit. That's crazy. Not what I want to see. All right. I think messed up something at my target here. I'm not sure what. Let me try this real quick. Well, actually, I'm gonna change my target here real quick. Cause it doesn't really matter now. God damn it. Cool. Let's open this shit in Binary Ninja. Let's see what the hell's going on here. Yeah, what the fuck is this shit? So it should work. B, C, D. Scanf. Not ref long enough? Or not one corpus, which is a problem. Okay, fine. I hate debugging fuzzers so much. Percent D. So like, what the fuck? Huh. Which was 8 with one second. Just taking info properly. Yeah. Hmm. 0. The fuck? Um. I have a better idea. This is just gonna be stupid. Um. Let's see. Oh, it's the other way around. There we go. I should find something now. There we go. Holy shit. Okay. All right. All right. Okay. Let me explain a few things why that was happening. So as you can see, we got a crash, which is cool. But all right. Let me explain what happened here. And why that first input was bad. 1, and 2, why this one worked. All right. I'll just let this one run for a while. Hopefully, it'll probably find some more crashes. So, all right. So, firstly, why that input was hard for fun, and this kind of comes back to the question of, um, so in terms of what fuzzers are, this kind of comes back to the question of what fuzzers are good at doing, and the real question is are what I guess what kind of bugs are, because a key question that is often asked in the fuzzing community is what kind of bugs are fuzzers good at finding, um, and the answer to that question is relatively shallow bugs, I want to say, unless you're using like grammar-based fuzzing, with that are fairly, and the more important part is fairly conducive to like standard mutation, like havoc mutation, like bit flips, and that kind of stuff. There's a lot of types of bugs that are just not very conducive to fuzzing, like specifically a lot of like heap bugs are often very hard to find with fuzzing. Specifically, at least bugs that are more introduced with like state changes as opposed to actual input. That's why fuzzers are really good at finding bugs. For example, in like media libraries, like libpng, for example, is a really big target. libtiff. What else? There's a bunch. libwebp as well. That because those inputs are like they're difficult to make, 1, and 2, it's very easy to mutate against those kinds of media libraries, which is why they're good to find. All right, let me explain why that first iteration didn't work. The reason that first iteration didn't work is because of how the input actually worked. So you recall, what I did is I did a scanf into a value here and compared that value, compare that val to. Now the reason this is hard is because we have to input this specific number, right? And what kind of ends up happening here is that, well, you have to convert, you basically input this number in decimal, so whatever this number is in decimal. And that's kind of hard to do, and it's kind of hard for the fuzzer to gain any kind of data on how to mutate your input further. And I'll explain kind of how that works with coverage. I'll explain that entire process. But the second input that we did was instead we input a string, and if it's A, B, C, D, then it crashes. The reason that's nice for a fuzzer is because the way we structured our program is that if it gets A, is that it only needs to get one. It doesn't need to get all four correct at once. It only needs to get one at a time. So if it gets A, then it essentially remembers that I got A, and then it only needs to get B. So then it gets B. Once it gets B, it remembers it has A and B. It knows that A and B are correct at this point. I'll explain why it knows it's correct. Once it gets B, it holds that in memory. Then you have to get C. Once it gets C, it finishes, goes to the next one. It remembers we have A, B, C, and then we get D. That's easy for a fuzzer to do, is to get 4 of them individually. Yeah. So let me explain kind of like the coverage process here, because that itself is a little bit complicated. All right. So I was going to kind of crashing it. All right. If I open this thing in binary, please. Yo, what the fuck? I'll get this. So if we open this in binary ninja here, actually, I'm gonna test target here. And, shit. Fuck. Let's start in Fire Ninja. You go to main real quick here. This is really complicated, but basically what's going on here is that what is this? What is this label? Oh yeah, okay, I know what's going on here. Okay, so I'm gonna run twice in the same if statement. That's actually interesting. That is weird. Why I'm the same input twice. Assembly here. Fuck. One, that's that. Wow. Okay. Yeah. So here's what's going on here. Basically, when we fuzz, we have this notion of a coverage map. The coverage map basically is an array of 8-bit integers, and every time. So let me show this off real quick. as well. This is the last presentation out of curiosity. Will. Is the last one cool? Okay, I don't actually give a shit then. Okay. So alright. So when we fuzz, we have this notion of a coverage map. So basically what that means is that it's basically just an array of 8-bit integers, so each is 8-bit. And each of these indices is associated with a different part of the program, with a different basic block of the program is what we call it. And when we hit that specific basic block, we increment the index associated with that basic block. So that's kind of how we keep track of coverage. Is that, for example, let's say we hit this one right here, then this one will go to, they all start at 0. If we hit the one associated with this one, we'll increment it to 1. If we hit this one, for example, we increment it to 2. I guess we increment this one to 1. That's kind of how we keep track of coverage. It's pretty, it's not too complicated. And this system is really effective because we essentially keep basically a total maximum of this coverage map of everything we've ever covered. And if we ever basically find, so for example, let's say this, for example, let's say this one right here, say this guy right here, we've never actually incremented this to 1, right? We've never actually hit the basic block associated with this value. If we find that, for example, in some run, this one goes up to 1, then we know that we found new coverage. And that input that we've inputted is not useful, so we remember it. That's kind of what we do here with our inputs. So for example, we take our if statement, we take our series of if statements. I guess I'll do it here actually. We go back to our target here. We take our series of inputs here. Now, every time we make it past an if statement, specifically, we increment it. We get new coverage in our coverage map, basically. So here we get new coverage. Here we additionally get new coverage. And after we hit the C, we also get new coverage. After we get this D, we also get this new coverage. And then we abort, which is a crash, basically. So as a result, you basically hit what I was talking about earlier, where you only have to find each letter once. Well, rather, you only have to find each letter individually, and you don't have to find them all at the same time. Because every time you find a new letter, you get the coverage associated with this guy. So for example, when it finds A, it gets new coverage, so it knows that that input that it found an A in is now useful. When it finds B, likewise, it remembers that an A and B led to new coverage. So it remembers that input. If it finds ABC, remembers that the ABC found new coverage. Same deal. Finds D, then remember that we found new coverage. And then we hit the crash, obviously. So that's kind of the coverage feedback loop. That basically just is the key to fuzzing. That's why fuzzing is effective. If we just did this dumb fuzzing, obviously we'd have to find A, B, C, and D all at once to find the crash. Yeah, that's kind of the key behind coverage-based fuzzing and why it's effective. I'm going to go over an in-memory example real fast. Yeah, let's see if I have that. Where did I put it? Maybe that's the bad files. Fuck. Let's see which one my fucking disk is. Nope, that's Samsung leaks. There we go. Yeah, I haven't moved that other one. Yo, what the fuck? update my fucking branch real quick. I don't know what I want. All right, cool. This is libafl. This is mainly what I work on. Yeah. This is mainly what I work on. I specifically work on the libafl Frida portion of it, and sometimes libafl. Actually, I really work on libafl too. Yeah. Sometimes some other parts, like libafl core. Sometimes work on that. But let me talk about a little about. Let me show the memory example real quick. VS Code here. Cool. So libafl is mainly in Rust, as you can see. Actually, I have 30 minutes. I could probably rip out a fuzzer real quick. Well, I'm just gonna modify this real quick. Yeah, okay. All right. So this right here is a fuzzer targeting libpng, which is a PNG parsing library. The way it basically works is that the point of libafl is you basically take everything that AFL++ has, and you split it up into components. So for example, for example, a good component is the edges observer. The edges observer basically is just keeps track of your coverage map. And top of your edges observer, you have a map feedback, which analyzes your coverage map to see if you have useful input. Time feedback, that's mainly used for I believe what is a time feedback used for? What is a time feedback used for actually? I have no clue. Is it just a timeout feedback? Should be. Oh, it just does nothing. All right. You also have objectives, so you have your crash feedback, see if there's a crash, timeout, see if it timed out. Here you have a state. It's just like the top level thing. That tokens. Here, right here, you have your mutator. This basically does all your mutations on your input. In this case, the mutation that we're using are Havoc. If you look at what Havoc actually is, Havoc is just a list of types. It's actually just like a tuple of a bunch of different. It's a bunch of really simple mutators, mainly like stuff like bit flip, byte, just like increment a single byte, negate a byte, add a word, add a D word, Q word. There's a bunch of just a bunch of really, really small mutators. It's just really, really fast is the point of it. You also have tokens. You have scheduler, you have your fuzzer. Yeah. Let me just run this real quick. So as you'll see with in process, I guess the key thing to keep in mind for in process is like way, way, way faster. Also, we are actually using in process here. As you can see, using in process executor, meaning we're executing everything in process instead of running things with a fork server. Yes. Cool. With PNG, a little while to make. Cargo, make. The cargo make run. Is that what it is? I don't remember. I want to say it was run. Cargo make run. Now, I guess the thing I do want to point out is with this case, we're not actually using, it's like in the previous case, we used AFL Clang Fast as our compiler. In this case, we're actually just using normal Clang. You can actually see that here. We use basically this thing called libaflcc, which is another wrapper for Clang, a little more customizable. You got libaflcc right here. All this really does is you add, this is the main thing right here. This is the fsanitized coverage trace PC guard. That just finds a what is that here? That just inserts coverage instrumentation. Very, very similar to what we see right here. This is also coverage instrumentation right here. Basically the same idea. It's gonna take a while to link actually. Oh well, it's just building libpng right here. Oh shit. Okay. It's cool to go over here. Is there anything else that's like worth going over? I guess another fun thing that we do here. This is really confusing. I still don't know why we do this. Actually, there's a purpose for it, but it's still really confusing. Instead of using main, you don't actually have a main function. You have a libafl main function, and the place where the main function is like deep in like libafl code. It's pretty funny actually. Your main function is right here. No, it's not right here. It's right here. Actually, I know exactly where it is. It's right here. So your main function is instead right there. You basically just end up running libafl main anyways, or your libafl run driver, your fuzzer run driver. That has led to a lot of confusing messages, a lot of really, really confused messages as to what the hell libafl main does. But yeah, that's kind of the point of libafl main. Oh yeah, there we go. Notice this right here. That's a shit ton of execs. I believe we only have one client, which is really good. I think this is single core. This is single core performance. Yeah. Earlier with AFL++, we were getting around 6K execs a second. Here we're getting around 100K execs a second. So you can kind of see like the substantial difference that using something like in process does. Because that fork, even though like one time it can be cheap, as you run shit at scale, you're trying to run things fast, that fork, that like small operation makes a massive difference. So that's why for the most part, most people who do fuzzing try to stick with in process because you just get, it was just that much of a difference. In fact, actually, this is the last thing. I don't know if we'll get any crashes here, but yeah, we are getting a lot. That's already like, what is that, like 10? Was that like 10 million execs or something ridiculous like that? Yeah, and it's been like what? Not that much time at all. So it's been like 2 minutes. So, like, I guess one final thing I can do is I can change our test target here to, instead of doing normal, instead make it persistent mode, which is nice. How the hell do you do persistent mode again? Persistent mode. I don't remember. AFL loop. It is just AFL loop. That's crazy. In this case, I make this instead persistent mode here. What this does here is, instead of, as I said earlier, instead of doing instead of reforking the process every time, it'll run that many execs in the process. It'll run, I guess, this 10,000 times. The 10,000 comes from there. Run this 10,000 times in the same process over and over again. We'll see a pretty substantial exec jump here, I think, at least. We should. C. We should see a. I'm sure I should compile it properly. Where's the sig? There we go. Sig AFL persistent. Cool. you can see, we had like a 6-time exec jump right there, like 36k execs. That's kind of the difference persistent mode makes. But even then, the forks still cost a lot. We're still like only a third of what in-process gives us. And that's kind of like the optimization game you play with fuzzing. That's why I think fuzzing is pretty fun. Honestly, if there's any questions, that was a lot. But any questions on any of this? That's kind of all everything I have for now. What's up? Yes. So a dumb fuzzer basically is a interesting. Anyway, the purpose of a dumb fuzzer is okay. So a dumb fuzzer basically just throw inputs at a target and hope it crashes. Right? It's like basically what you built in 201. It's very similar to that. Instead, here we have a slightly smarter fuzzer, a coverage-based fuzzer. The point of that is to instead of just throwing inputs and hoping something happens, we instead collect some kind of telemetry on the actual target, and that telemetry is coverage. And as we build coverage, we basically, well, the purpose of coverage-based fuzzing is, as a high level, is basically to find inputs that generate more coverage in the target that get farther into the target. Because obviously you want to have as much coverage on the target as possible if you want to find crashes in the target. You want to cover as much as code as possible. So coverage-based fuzzer is really, really good at walking through a target and trying to find something. That's really the purpose of it. Yeah, that's better. All right. Any other questions? All right. Cool. That's it for me.